So hello everyone, in this video we'll be solving another LeetCode problem, and the problem name is balance a binary search tree. So given the root of a binary search tree, return a balanced binary search tree with the same node values. And if there exist more than one answer, you can return any of them. And then they have said that a binary search tree is balanced if the depth of two subtrees of every node never differs by more than one. So the problem statement is pretty much straightforward. You are given a binary search tree. You need to convert it into balanced binary search tree. Now what is a balanced binary search tree? Balanced binary search tree means that for every node, the left subtree and the right subtree, the number of nodes, their difference should not be more than 1. It should be always less than equal to 1. For each and every node. So there is a left part, there is a right part. So for this root, the left and the right nodes difference should be at most 1. Similarly, if we have nodes something here, it will also have some left part, it will also have some right part. So for this node also, it should hold the property of balanced part. So for each and every node, we need to check whether this left subtree and the right subtree, the difference between them, the number of nodes should be less than equal to 1. So this is what balanced binary search tree is. Now if you still don't understand what is this balanced and how do we get the balanced part, you can watch yesterday's video. I will attach it in the top right corner, so it will be more easier to understand this particular problem as well. So you can watch that video out. So in this question and the previous question, the difference is only that you need to convert the BST into a balanced BST. In the previous problem, we just need to tell true or false whether it is a balanced binary tree or not. Here we have been given binary search tree and we need to convert it into balanced binary search tree. So first of all, there are two things that we need to do in this question. We need to convert a BST first by binary search tree, and then we need to also take care that it is balanced. So first of all, how do we create a binary search tree? How do we create a binary search tree? And also don't forget the tree which is being given to us, that is also a binary search tree. So in order to create a binary search tree, first we need the sorted order, right? We need the sorted order of all the nodes. So let's say we take any random sorted order, let's say 1, 2, 3, 4, 5, 6, 7. Now let's say we need to create a binary search tree. So let's say we take this element as a root node, this element as a root node. So let's say 4 is the root node. Now you can see here, the left part has all the lesser elements than it, and the right part has greater element than 4. So this is the property of binary search tree, right? For a particular root node, all the elements towards its left should be lesser than the root node, and all the elements towards the right should be greater than the root node. This is the property of binary search tree, right? So if you see the sorted order and you pick the node 4, you can see it will hold the property of binary search tree, right? All the elements towards its right, on the left are lesser than 4, and all the elements towards the right are greater than 4. So we can create recursively binary search tree with the help of this sorted order. But how do we get this sorted order? How do we get the sorted order? So let's say we are given a binary search tree like this, 1, 2, 3 and 4. So you can see there is nothing to left, so we don't need to compare anything. This is the root node and every element towards its right is greater than the root node. So we can say that okay, this is a binary search tree. So this will be given to us. Now how do we get the sorted order from this? Now if you know in-order traversal, what is in-order traversal? In-order traversal means we will first cover each and every left node, then we will cover the root, and then we will go towards all the right nodes. So in this order we will traverse. So this traversal is known as in-order traversal, going to the left, then root, and going to the right. So in this, if you go towards left, then root, then right, what we will get in BST, not this particular example, but in general BST. So there is nothing to left, so we will take root as the first element. So okay, root as the first element, and then we will go towards the right. So first element is 2, then the second element is 3, and the last element is 4. So if you traverse in order, if you do the in order traversal on the BST, you will always get the sorted order. You will see, you will always get the sorted order. So one problem is solved. We need to get the sorted order. We will apply in order traversal on the given input of the binary search tree, and we will get the sorted order with the help of this in order traversal. Now in this sorted order, it will help us create a binary search tree again, because we have already seen, if we pick any element, all the elements towards its left will be lesser than it, and all the elements towards its right will be greater than it. And we can do this recursively to build a BST. So we will be able to build a binary search tree again with the help of this sorted order. But how do we create a balanced binary search tree? That is the problem. So how do we handle this balanced part? So let us see this same example again. So if you see the example 1, I have taken example 1 only. So if you see, this is the example 1. So this is the BST that is been given to us, and if you see, there can be two possible outputs. Either this can be the balanced BST, or this can be the balanced BST. So this can be the balanced BST. We can return any of them. And why it is balanced BST? Obviously, first of all, it is a BST in itself. You can see this is the root, left is lesser than the root and rights are greater than the root. Here also this is the root, left is lesser than the root and right is greater than the root. For this node also there is nothing towards the left and right is greater than the root. So it is a BST. But how it is balanced? Because the left subtree, the number of node is 1, and the right subtree, the number of node is 2. So difference between them is 1, which is less than equal to 1. So it holds the property of balanced part also. Same here also. If you look at the left subtree, we have number of elements 2, and if you look at the right subtree, you have the number of elements as 1. So if you take the difference between them, you will get 1 only, which is again less than equal to 1, which holds the property of balanced part. So it is a binary search tree and it is balanced. So we can say that okay, it is a balanced binary search tree, and you can return any of them as an answer. So we have actually solved the problem for the sorted order part, and from the sorted order part we will get the binary search tree again. But how do we get the balanced binary search tree? So let us see now. So first of all, we are sure that we will have the sorted order, right? We will have the sorted order 1, 2, 3 and 4. So if we have the sorted order, we will have the binary search tree for sure. We will have the binary search tree for sure. Now we need to also take care that this particular binary search tree is also balanced. So what is balanced? Everything on the left part and everything on the right part, the number of nodes should be differ at most by 1. So what is the best possible scenario to take a root element? We will take the root element that is middle of this entire array. So let's say we take 3 as the root node. So let's say let me just erase this entire part. So let's say we take 3 as a root node. So okay, 3 as the root node. Now we see that okay, the left part has 2 elements and right part has 1 element. The difference is at most 1 only here also. So you see, if we take the middle element, we are getting the balanced part. Now why this middle part is working? Because if we have the odd number of elements, if you take the middle element, the left part and the right part will have same number of elements. If we will have same number of elements, let's say 1, 2, 3, 4 and 5. So if you take 3, the left part has 2 elements, right part has 2 elements. But if it has even number of elements, if you take the middle element, let's say this 2 or this 3, whatever you take, let's say we take this 3. So its left has 2 elements and right has 1 element. So it will have the difference of at most 1, which will surely hold the property of balanced binary search tree. So it will work in even case also and it will work in odd case also. So that's why we take middle element, so that we have equal number of, or as we have more chances of getting equal elements towards the left and right path both. So that's why we are taking middle elements always. So let us do the entire thing again. Let's say we have this particular array 1 2 3. Okay, 1 2 3 and 4. This is the index 0 1 2 3. So we can do it in terms of like binary search also. We can have a low element, we can have a high element, and we will find the middle element. So middle element will be what in this case? Low plus high by 2. So 0 plus 3 by 2. So what we will get? 3 by 2, which is nothing but 1. So we will take 1 as the middle element. So this index 1 will be the middle element. So we will take 2 as the middle element. So okay, 2 will be the root node. Now you see the left part has 1 node and the right part has 2 nodes. So the difference is at most one only. So you see it holds the property of balanced part. And obviously if you are using a sorted array, it will obviously create the BST for us. So it will create balanced BST for us. So this is the 2. And now what we will do? Now you see on the left part we have this one element, and on the right part we have this these two elements, these 3 and 4. So we will make BST for we will make balanced BST for this using recursion. So we can consider this whole array as the new array again. As we were considering this entire array, we will consider these two separate arrays, this array and this array, as new array, and we will solve this problem recursively. So we have this root node, we have this left part, and we have this right part. So now we will solve this problem for the left part recursively and right part recursively. So let's say we have this right part. So let's say let me just erase this entire thing again. So yeah, we have this right part. So now what is the index of index here? Index is here 2 and index is here 3. So our low will be pointing to here and our high will be pointing to here. So let's say what will be the mid element? Mid element will be nothing but 2 plus 3 by 2. So it is nothing but 5 by 2, and it is nothing 2 only. So we will take this as the middle element. So we will create this as the node, and we will create the balanced BST towards its left part and right part recursively. So what we will do? So let me erase this thing again. So now what will happen? We had this particular thing 3, 4. So this will be the root node now. So okay, this will be the root node, and whatever is on the left will come on the left subtree, whatever is on the right, it will come on the right subtree. So there is nothing towards its left, so its left part will be empty, and its right part has 4, so it will come 4 here. So now we will again solve this problem recursively. So here at this moment, low and high are both at the same particular index. What is the index? Index is nothing but 3. So we will say mid element will also be 3 only, and this will be the root. So we can make this mid element as the root. So we'll say okay, 4 will be the root node. Now if we have only one element and that is the root node, there is nothing towards its left and nothing towards its right. So that means it is the end of the recursion. So we can move back from here, and then we will we will solve this particular sub problem. So here also you can see there is only one element remaining. So its low and high pointer will be pointing to here only, and mid element will also be pointing to here only. So we can create this node, this mid node as the root node, and we can solve it recursively. So what we will do, we will be having 1 here. So we will create 1 as the root node. So 1 as the root node, and this is the array, right? So there is nothing towards its left and there is nothing towards its right. So we will stop our recursion here. So you see, we have completed our recursion also, and whatever result we get, this result we get, it is a BST and it is a balanced BST. Its left subtree has one element and its right subtree has 2 elements for this particular root node. We will check for each and every node, but yeah, we are starting from the root node. So yeah, you see it has left part has 1 and right part has 2 elements. So this root node follows the property of balanced part. If you take this element, it has nothing towards its left, it has nothing towards its right, so it already satisfies the property of balanced part. If you take this element or this node, it has nothing towards its left part, it has one node towards its right part. So again it satisfies the property of balanced part, because left has 0 and right has 1, so difference is again at most 1. If you take this element as the root, you see there is nothing towards the left and nothing towards the right, so again it is balanced because both are 0 0. So you see this entire binary tree is balanced, and this binary tree is in itself a binary search tree. So you see the left, all the elements towards the left are lesser than the root, all the elements towards the right are greater than the root for each and every node, you can see. So this is a balanced binary search tree, and if you look at the output of the this particular input, you will see this is the same output that we are getting. So you see this is the same output that we are getting, 2 1 3 4, the same that we have created here. Yes, 2 1 3 and 4. So this is how we'll be solving this problem. So let me just summarize it, what we are doing again. So let me write the summary here. So what is the summary? First, get the sorted order in array with the help of in order traversal. After getting the sorted order, what we need to do? We need to apply some kind of binary search thing, so that with the help of low pointer, high pointer and mid pointer, we can create balanced BST recursively. So recursively, by keeping the mid node always the root element. So if the middle node will be the root element, we will always be sure that okay, we will be getting the balanced binary search tree. So these are the two things that we need to solve in this particular problem. So let us see the code now. So yeah, this is the code. So if you see, first of all we need to get the sorted order. So sorted order will be getting with the help of in order traversal. So I have given the array name as in order because we will getting the sorted order with the help of in order traversal. So then we are calling this function get sorted order, which will take the root element and this in order array, so that we can get the entire array in sorted order with the help of this given BST. So we will apply in order traversal in this function. So let us see what is this function. So you see, this is the function. So what we are doing here, if there is no root, simply return, otherwise go towards the left, then root, then right. So this is what in order traversal is. So first go towards the left, then take the root, and then go towards the right. So this is what we are doing in the sorted order, and we are always pushing the root elements towards inside the in order array that we are taking, so that we can get the sorted order inside this particular array. So the first part is solved. We got the sorted order. Now after getting the sorted array, let's say this is the sorted array, what we need to do? We need to get the balanced binary search tree from this. Now if it is sorted, we will always get the BST with the help of recursion. But how do we get the balanced BST? We will always try to pick the middle element. So we are declaring low pointer, high pointer, low as 0, high as the size of this array -1. So low will be pointing to here and high will be pointing to here. And now we are getting the balanced binary search tree by calling this function. So we are calling this function, and what is this function? It will take low pointer, high pointer and this sorted array. Now we always need to pick the middle element and then solve this recursively for this left subtree and right subtree. So this is the base condition. If our low is greater than high, return null from here. We have already like created the BST or the balanced BST. That's why the pointers get exchange or override each other. So this is the base condition. Then we need to pick up the middle element. Middle is nothing but low plus high by 2. So with this we will get the middle element. Now we will have the middle element. So obviously we will create the root node for this middle element. So what we were doing, we have this 3, we were creating this root, and then we were passing this particular 1 and 2, or in that case we had 2 at the middle element. So let us create that only. So we had 2 as the middle element, not 3. So its left subtree has this array and its right subtree has this array. So we were solving these two subproblems or these two left subtree and right subtree with the help of recursion. So we have created the root node. Now we need to solve this recursively for the left part and right part. So we are again calling the balanced BST, and what will be the left part? Left part will be nothing but from low to mid minus 1. So from low to mid minus 1. And what will be the right part? The right part will be nothing but mid plus 1 to high. So mid plus 1 to high. So we will solve this recursively, and in the end we are returning this root node, which will be the nothing but the root of the balanced BST. So you see, we have the in-order traversal, and with the help of in-order traversal we have got the sorted array, and with the help of sorted array we have created the balanced binary search tree. So this is how we'll be solving this particular problem. So I hope you understand this problem. Thank you for watching.